Based on what you were describing, this could soon be the biggest story in the world. Literally the biggest story in the universe.
Something absolutely remarkable just happened that's sending shockwaves through the astronomy community. A Japanese astrophotographer, using equipment you could buy online right now, has captured what experts are calling the clearest and most detailed image of interstellar comet 3I Atlas ever taken by a non-professional observer. We're talking about an image so sharp, so revealing, that it's forcing scientists to confront details they've been debating for months. Paul Kargs captured this extraordinary photograph on November 26, 2025, at 1925 UTC using a half-meter telescope, and what it shows is stopping researchers in their tracks. The image reveals a tightly collimated antitail extending over 1 million kilometers toward the sun, alongside a massive tail stretching 5 million kilometers in the opposite direction, both displaying structure and clarity that professional observatories are struggling to explain. What makes this even more extraordinary is that multiple amateur astronomers across 3 continents, from Spain to Chile to the United States, are all capturing images showing the exact same impossible features, meaning this isn't a camera glitch or processing error. This is real, it's happening right now, and by the end of this video, you'll understand why Harvard astrophysicist Avi Loeb just published calculations showing these amateur images contain data that fundamentally challenges our understanding of how natural comets work. But before we dive into what these images actually reveal, make sure you hit that subscribe button and turn on notifications, because 3I Atlas reaches its closest approach to Earth on December 19th, just 3 weeks away, and the data coming in between now and then could rewrite astronomy textbooks. And if you're as blown away by this as I am, smash that like button to help spread awareness of what might be the most significant astronomical discovery in human history. Let me set the context for why these amateur images are creating such intense debate. Since 3I Atlas was discovered on July 1st by the Atlas Survey Telescope in Chile, it's been observed by virtually every major telescope on Earth and in space. NASA's Mars Reconnaissance Orbiter captured images from 30 million kilometers away in October. The Hubble Space Telescope imaged it in July. The James Webb Space Telescope conducted detailed spectroscopic analysis in August. Professional observatories have been tracking this object with equipment worth hundreds of millions of dollars. But here's what's absolutely fascinating. The clearest, most detailed view of 3I Atlas's jet structure didn't come from any of those professional instruments. It came from a dedicated amateur astrophotographer in Japan using a telescope with a half-meter aperture, the kind of equipment serious amateur astronomers can actually afford. Mitsunori Tsumura's image, taken on November 22nd, shows detail that's making professional astronomers take notice because it reveals features they've been trying to confirm for weeks. The image clearly shows both an antitail pointing toward the sun and a much longer tail pointing away, both tightly collimated, both maintaining structure across millions of kilometers of space, and both defying straightforward natural explanations. But here's where things get really interesting. This isn't just one person with one image. On November 17th, French astrophotographer François Kugel captured stunning images using a 0.4-meter telescope, combining 22 exposures of 30 seconds each. On November 16th, Satoru Murata in New Mexico released an image combining 24 60-second exposures with a 0.2-meter telescope that shows multiple jets in extraordinary detail. Then on November 22nd, Peter Carson Lee in Spain used a 0.315-meter telescope to capture images consistent with the same jet morphology. A day later, on November 24th, Elena Walter in Chile, using a 0.432-meter telescope, photographed the exact same structures. And perhaps most remarkably, on November 16th, Stuart Atkinson in Kendal, England, captured 3I Atlas using a Seastar S50 Smart telescope, a device that costs around $500 and has been mockingly called a toy by some professionals. Think about that for a moment. An object that formed around another star billions of years ago, that's been traveling through interstellar space for potentially millions of years, is now close enough and bright enough that backyard astronomers with consumer-grade equipment are capturing scientifically valuable data. We're watching amateur astronomers contribute meaningful observations to one of the most important astronomical events of our generation. And the mystery deepens when we look at what these images actually show. Avi Loeb has analyzed Tsumura's November 22nd image in detail, and the numbers he's calculated are genuinely startling. Given that 3I Atlas is currently 300 million kilometers from Earth, the apparent size of the features in the image translates to real physical dimensions that are difficult to explain naturally. The tail extends approximately 5 million kilometers, while the antitail, pointing toward the sun, extends about 1 million kilometers. Now here's what makes this so problematic. For that antitail to maintain its structure while pointing directly into the solar wind requires enormous momentum flux. The solar wind at 3I Atlas's location is flowing at about 400 kilometers per second, which is at least 1,000 times faster than the thermal speed of gas outflowing from a natural comet. Since ram pressure, the pressure exerted by moving fluid, scales with the square of velocity, this means the mass density in the outermost parts of the antitail must be roughly 1,000,000 times greater than the solar wind density. For a natural comet to maintain an antitail that pushes through the solar wind that requires a mass loss rate of approximately 200 tons per second per square area, measuring about 300,000 kilometers on a side. When you account for both the tail and the antitail, the total mass loss rate over the past 2 months comes out to roughly a few billion tons. Wait, there's more to this story that makes the numbers even more concerning. Back in September, Loeb calculated the minimum mass of 3I Atlas based on the fact that it showed no non-gravitational acceleration during July, August, and September. Any such acceleration would come from asymmetric outgassing producing thrust, and the amount of acceleration depends on the mass loss rate, the speed of the outflowing gas, and the total mass of the object. His calculation suggested a minimum mass of about 33 billion tons. The mass loss required to produce the jets visible in these amateur images amounts to roughly 10% of that minimum mass over just 2 months. That's an extraordinary amount of material to lose in such a short time without the comet visibly fragmenting or disintegrating. Professional observations indicate that 3I Atlas has maintained its structural integrity. It hasn't broken apart like many comets do when they lose significant mass rapidly. The nucleus appears intact despite supposedly shedding billions of tons of material. For natural comets, losing 10% of their mass in 2 months typically results in fragmentation events that would be obvious in observations. We're not seeing that with 3I Atlas. Now here's where the story takes a dramatic turn into deeply controversial territory. Loeb has noted that if the jets aren't produced by natural sublimation of ice, if they're instead coming from technological thrusters, the required mass loss drops dramatically. Chemical thrusters, like the kind we use on spacecraft, produce exhaust velocities much higher than thermal outgassing from ice. Since the required mass loss scales with the square of the velocity ratio, chemical thrusters would reduce the needed mass by 2 orders of magnitude, or about a factor of 100. Ion thrusters, which produce even higher exhaust velocities, would reduce it by 4 orders of magnitude, a factor of 10,000. In other words, if those jets are technological in origin, you could produce the same thrust effects visible in the amateur images, while losing only a tiny fraction of the mass required for natural outgassing. The object could maintain its structural integrity indefinitely while producing precisely controlled jets for trajectory adjustments. This is speculative, absolutely, but it's based on solid physics and engineering principles we already understand. If you're still watching, remember to hit that like button, because what I'm about to tell you next connects these amateur images to something even more extraordinary. The non-gravitational acceleration that these jets are producing has been measured by NASA's JPL Horizon system, which incorporates data from about 230 different observatories worldwide. The detection is now statistically significant at 10 standard deviations, meaning it's absolutely real and not a measurement error. The acceleration value is 5 times 10 to the negative 7th astronomical units per day squared. That might sound like a tiny number, but it's precisely the right magnitude to have altered 3I Atlas's trajectory by about 0.1 million kilometers during its passage near the Sun in late October. And here's the kicker. That course correction brought the comet's closest approach distance to Jupiter, scheduled for March 16, 2026, to precisely 53.445 million kilometers, which is identical within measurement uncertainty to Jupiter's Hill radius of 53.502 million kilometers. The Hill radius is the boundary of Jupiter's gravitational sphere of influence, the region where Jupiter's gravity dominates over the Sun's, making it ideal for placing satellites in stable orbits with minimal fuel requirements. The probability of this being a coincidence is approximately 1 in 26,000. The amateur images are capturing the mechanism by which this precision trajectory adjustment is being achieved. The tightly collimated jets, visible in multiple independent observations from different locations, are pointing in directions that would produce thrust vectoring. Unlike typical cometary outgassing, which tends to be more diffuse and omnidirectional, these jets maintain narrow focus across enormous distances. The November 17th image from Francois Kugel shows multiple distinct jets emanating from the nucleus, each maintaining directionality. The November 16th image from Satoru Murata reveals that some jets point toward the sun while others point away, and still others appear to be oriented at different angles. This isn't the pattern you'd expect from a randomly shaped, naturally outgassing comet nucleus. Natural comets typically have jets that correspond to active areas on their surface where ice is being heated by sunlight. As the comet rotates, those jets sweep around like sprinkler heads. But 3I Atlas has a confirmed rotational period of 16.16 hours, and yet these jets maintain their orientation despite the rotation. That's one of the documented anomalies that makes this object so puzzling. Make sure you're subscribed with notifications turned on, because what happens over the next 3 weeks could be absolutely historic. On December 19th, 3I Atlas will make its closest approach to Earth at a distance of 269 million kilometers, about 1.8 astronomical units. That's still very far away, almost twice the distance to the Sun, so there's absolutely no danger to Earth. But that close approach means observing conditions will be optimal. Amateur astronomers around the world are organizing coordinated imaging campaigns. Professional observatories are allocating telescope time. The James Webb Space Telescope has scheduled follow-up spectroscopic observations for December that will specifically target the jets. Those spectroscopic measurements will reveal the velocity and composition of the material in the jets. If they're produced by naturally sublimating ice, the spectrum will show specific signatures: water vapor, carbon dioxide, carbon monoxide, all expanding at thermal velocities determined by how hot the gas is. Typical speeds for naturally outgassing comets are a few hundred meters per second. If the jets show significantly higher velocities, if the composition is unusual, if there are chemical signatures inconsistent with natural ices heated by sunlight, that would be extraordinarily significant evidence that something else is happening. The images these amateur astronomers are capturing right now are going to be studied and analyzed for years, possibly decades. Think about the historical significance of what's happening. Throughout most of human history, astronomy was the domain of a privileged few with access to rare instruments. The discovery of Neptune, the mapping of Mars, the detection of distant galaxies, all of this required professional equipment and institutional support. But we're living in an era where dedicated amateurs, with commercially available telescopes costing a few $1,000s, or in Stuart Atkinson's case, just $500, can capture scientifically valuable data on an interstellar visitor. The democratization of astronomy means that discoveries aren't limited to professional observatories anymore. The clearest image of 3I Atlas's jet structure came from someone's backyard in Japan. That person, Mitsunori Tsumura, probably has a day job completely unrelated to astronomy. He's not on the staff of a research university or a space agency. He's an amateur in the best sense of that word, someone who does it for the love of it. And yet his image is being cited by Harvard astrophysicists and analyzed by professional astronomers trying to understand this object. The scientific community's response to these amateur images has been fascinating to watch. Some researchers are embracing the contributions, recognizing that the collective observations from dozens of amateur astronomers provide continuous monitoring that no single professional observatory could match. Others are more cautious, noting that amateur equipment may not be as well calibrated as professional instruments, and image processing by non-professionals might introduce artifacts. But the fact that multiple independent observers using different equipment in different locations are all seeing the same structures makes it very difficult to dismiss these observations. You can't claim they're all making the same processing mistake or experiencing the same equipment malfunction. The consistency across independent observations is powerful evidence that what they're capturing is real. Peter Carson Lee in Spain, Elena Walter in Chile, Francois Kugel with his 0.4-meter scope, Satoru Murata in New Mexico, Mitsunori Tsumura in Japan, Stuart Atkinson in England with his $500 smart telescope. They're all documenting the same phenomena. The honest answer is that we're in unprecedented scientific territory. Never before have amateur astronomers been able to contribute meaningful data to the study of an interstellar object. The previous interstellar visitors, Oumuamua and 2I/Borisov, were either too faint or too fast-moving for most amateur equipment to capture useful images. But 3I Atlas is bright enough, slow enough relative to background stars, and positioned favorably enough that backyard astronomers can actually contribute to our understanding of it. The images they're capturing contain information about jet structure, mass loss rates, temporal evolution of the coma, all of which helps constrain theoretical models. Whether 3I Atlas turns out to be an extraordinarily unusual natural comet, or something that challenges our assumptions about what's possible, the amateur astronomy community will have played a crucial role in documenting its behavior. That's a remarkable testament to how far astronomical technology has come and how accessible it's become. Drop a comment below with your thoughts. If you have a telescope, even a small one, have you tried imaging 3I Atlas? What do you think these jets actually represent? Natural outgassing, or something we haven't fully considered? Share this video with anyone who loves astronomy and citizen science, because what we're witnessing is the democratization of space exploration in real time. The fact that a random person with a backyard telescope can capture the clearest image of an interstellar visitor, contributing data that Harvard astrophysicists analyze and cite, shows that the barriers between amateur and professional astronomy are breaking down. We're all part of this discovery process now. The next 3 weeks, as 3I Atlas approaches Earth and more observers capture more data, will be absolutely crucial. Whatever this object turns out to be, we're fortunate to be alive at exactly the right moment to witness it, to study it, and to participate in unraveling its mysteries. Until next time, keep looking up, keep capturing data, and remember that you don't need a multi-million-dollar telescope to contribute to humanity's understanding of the cosmos. Sometimes all you need is clear skies, a few $100s of equipment, and the determination to point your camera at something nobody fully understands yet.